Hello student. In today's session, we start chapter number 14, dual nature of radiation and matter. So very easy chapter, very important chapter and scoring chapter from the 12th standard syllabus. Now let me start with the introduction. So according to the classical theory, light is an electromagnetic wave. Light is an electromagnetic wave. Optical phenomena which are followed by the light such as interference, diffraction, polarization suggests that light is having wave nature. We already learned Huygens wave theory of light. After that, we learn interference, diffraction, polarization. We can explain all these phenomena by considering light is a wave. However, the phenomena of black body emission. So we talk about the black body emission could not be explained on the basis of wave nature of light. If we consider the wave nature, we cannot explain black body emission as well as the many other phenomena also. Max Planck's 1901 proposed the quantum theory of light. Scientist Max Planck proposed a quantum theory of light to explain the black body radiation. In interaction of radiation with matter, radiation behaves as if it is made of particles called as photon, and that particles are called as quantum. Photon or quantum. This radiation possesses dual nature, wave nature as well as particles. Radiation possesses dual nature. Dual means it has a wave nature as well as it has a particle nature. On the basis of symmetry, scientists de Broglie proposed a de Broglie hypothesis. As per that hypothesis, he used the symmetry of the nature and he proposed that a radiation has a dual nature. Now after that, we have to start what is photoelectric effect. So this is a very important concept, photoelectric effect. So photo means it's light, electric effect. So in this, the phenomenon of emission of electron. So here, emission of electron from surface of metal when light of suitable frequency is incident on it. It is called as photoelectric effect. You can see here. So this is metal, and this is a radiation. When this radiation of suitable frequency incident on the metal, from the metal surface, electrons are knocked out, and that phenomena is called as photoelectric effect. These electrons emitted are called as photoelectrons. So these are the photoelectron, and the current flows is the photoelectric current. All metals emit photoelectrons when radiated with UV light. So all metals emits the electron when it is radiated with UV light. Means it shows all metal shows photoelectric effect for UV light. But some alkali metals such as sodium, potassium, cesium are photosensitive to visible light. When visible light incident on the sodium, potassium, then they shows the photoelectric effect of that light also. This photoelectric effect was discovered in 1887 by Heinrich Hertz. You remember who discovered the photoelectric effect? It is discovered by Hertz. Now here we have to learn experimental study of photoelectric effect. So let's see the experimental arrangement for photoelectric effect. So here you can see a diagram. So this diagram shows the experimental arrangement for photoelectric effect experiment. Now let me discuss the experimental setup. So it consists of evacuated glass tube. So evacuated glass tube. You can see this is a glass tube. So evacuated glass tube fitted with quartz window. So you can see a quartz window here. So this is a quartz window. Two disc-shaped metal electrodes called emitter, it is shown by E, and collector plate C. So this is E for emitter C for collector. These are the two electrodes fixed at two ends of the tube. So this E is at one end and C is at another end. The emitter plate is coated with material whose photoelectric emission is to be studied. This emitter plate means this E is coated with photosensitive material. A battery keeps the collector plate at positive potential. So this battery keeps this is at positive potential with respect to this emitter. A rheostat is used as a potential divider. You can see this is a rheostat. So this part is a rheostat. It is used as a potential divider. So to vary the potential, and it allow to change the collector potential V with respect to the emitter. So we can change the positive potential. We can make it more positive. We can make it less positive by using that rheostat. UV light from variable frequency. So UV light from variable frequency and intensity. Then UV source S is made is incident on emitter plate through quartz window. So listen, so this is source of the light, source of UV light basically. So this UV light is may allow to fall on this emitter plate, and this UV light is having a variable frequency, different frequency. We can change the frequency, we can change the intensity also. That kind of arrangement is there. The photoelectrons are emitted. So when the UV light is incident and photoelectron, you can see these are the photoelectrons. Photoelectrons are emitted by the emitter, are collected by the collector plate. The photoelectric current flowing through the circuit is measured by microammeter. So here you can see this is a microammeter. This measures the current. So why microammeter? Because it's a very small current. So we are using microammeter to measure this current. Now you can remember this diagram here. So we are using this device. So this is glass tube. Then this is quartz window through which UV light is allowed to fall. Then this is emitter, which is coated with photosensitive material. This is collector, which collects the electron, and because of that we get the current in this microammeter. So this is a rheostat. By using that we can vary the potential. Let's see experimental procedure. The collector is kept positive potential. Collector is kept at positive potential with respect to the emitter. The intensity of UV light is kept constant. Intensity we are keeping constant and frequency gradually increased. So I can draw a smaller diagram here. You can see here. This is window. This is emitter plate, and this is collector plate. So here collector is a positive and with respect to this emitter. So when the light is incident here, electron is emitted. But initially we are keeping intensity constant, intensity and means intensity constant, and frequency we are increasing gradually. It is found that when the frequency is less, no current. So this is microammeter, no current in the microammeter, means no electrons are emitted at low frequency. As we start increasing the frequency, then also no current. At one particular value of the frequency, we get a current. That minimum value of the frequency is called as threshold frequency. Threshold frequency. So means photoelectric threshold frequency I can represent by mu 0 and frequency by mu. So when the frequency is greater than threshold, that time only the photoelectric effect is observed. When we adjust the frequency of radiation greater than threshold, then only we can see a photoelectric effect, otherwise no photoelectric effect. So initially, if you want to write everything in a graphical way, we can write like this way. So this is a y-axis. Here we can take photoelectric current, and here we can take frequency. So initially, when zero frequency, no photoelectric current. As we start increasing frequency, then no current. But at one particular minimum value of the frequency, we get a current, that is threshold frequency. Then after that, as we increase the frequency, we get a photoelectric current. So here, this value of the frequency is called as threshold frequency. Threshold frequency means, remember, the minimum frequency at which photoelectric emission just begin is called as threshold frequency. And threshold frequency different for different material. So it depends on the material basically that you have. Then after that, the intensity. Now, intensity of light is now made very weak. Now we decrease the intensity. It is found that photoelectrons are emitted instantaneously. Photoelectrons are emitted instantaneously. There is no time lag between beginning of radiation and emission of photoelectron. Means, listen, as we made the intensity of incident, ultraviolet light is now made weak. Then we can see a little less photoelectrons are emitted. So there is no time lag. As we decrease or increase the intensity, at the same time we observe the change in the photoelectric current in short. So there is no time lag. So we can write in single line this as a photoelectric effect is an instantaneous process, no time lag. Now third point, frequency of incident UV light. Now frequency constant. See here, frequency is constant. At a value greater than threshold value, means frequency we are keeping greater than threshold frequency, and intensity we are gradually increasing. Intensity we are increasing. Then it is observed that photoelectric current increases. As we increase intensity, it is observed that photoelectric current increases. So we can write it in a graphical way like this. You can see intensity of light and photoelectric current. So as intensity increases, photoelectric current increases. So you can write it here, photoelectric current proportional to intensity. Photoelectric current is directly proportional to intensity. Means more the photoelectric current you want, more the intensity of light must be there. Now next, frequency as well as intensity of incident world light is kept constant. Both intensity we are keeping constant, frequency is constant. The positive collector potential, now we are changing the potential. Potential increased. Which potential? You note here, positive potential we increase. So we increase positive potential. So we made it more positive. Then what happened? You can see here in a diagram. So this is diagram. Okay. So this is emitter and this is collector. So as we make it more and more positive, then the electrons, this collector attracts more electron, means attract electron very fastly, because more positive charges are more positive potential develop on this collector. So slightly the photoelectric current increases. So we can see here there is a slight increase in the photoelectric current. But here the number of electron in this region is constant. So later on this current remains constant. So it increases up to a particular value and then it is a constant, and that current is called as saturation current. Beyond that it cannot be increased. Saturation current means the constant value of the photoelectric current. When we make this collector more positive, that constant value is called as saturation current. Now after that, next point, if intensity of radiation is increased, now intensity is increased, frequency is constant, then it is of intensity increases means photoelectric current increases. Then it is found that saturation current increases. Saturation current increases. And saturation current proportionally increases with the increase in intensity. You know that current and intensity, photoelectric current and intensity, they are related. They are proportional to each other. So as intensity increases, saturation current also increases. Now next one, if the positive collector potential is gradually reduced. Now we are reducing the positive potential to zero. So as we make the potential zero, then it is found that the photoelectric current also decreases. It decreases, that you know, not coming zero. So however, even the collector is at zero potential, some photoelectric current flows through the circuit. So then also we are getting some photoelectric current. Now potential is zero, then also some photoelectric current we get. Now we make it negative. The collector is now gradually negative. So we can make it negative. It means that you can see in this diagram. So this is diagram. This is glass tube. So here, if we make it more and more and more negative, then these electrons in this region are repelled by this negative plate. So when it is zero, that time some photoelectric current we get here in the microamp. But as we make it negative, then electrons are repelled. As electrons are repelled, the current decreases. If we make it more negative, more repulsion, more negative, more repulsion. At one negative potential of this collector, photoelectric current is zero, and that is called as stopping potential. Stopping potential means at one negative potential of this collector plate, this photoelectric current becomes zero, and that negative potential is called as stopping potential. In previous examination, question is asked, what is stopping potential? So you have to remember the definition of stopping potential. So it's a negative potential for which photoelectric current is zero, is called as stopping potential. Now you can see here a diagram for this. So here, so you get here a saturation current 1, 2, 3, because three different intensities are there: low intensity, high intensity, and mid intensity. We change the intensity, we get the different saturation current. But as we make it negative, 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 then at one particular stopping potential, means here we get stopping potential. Negative potential, the current is zero, and that is the stopping potential. So stopping potential does not depend on the intensity. Intensity we change three times. You can see 1, 2, 3. But then also all the time we get the same stopping potential. In stopping potential does not depend on intensity. This is the conclusion. Now, let's see. Now, if frequency increase, now we are changing the frequency. Frequency increased. Now, intensity we have to constant. Intensity constant means we get photoelectric current constant. And the same experiment we have to do. It is found that stopping potential increased linearly with the increase in frequency. We get a different stopping potential. Now, in previous one, frequency is constant, so we get the same stopping potential every time. But now frequency increase, so we get increase in the stopping potential also. Thus, the maximum kinetic energy ejected by photoelectron increases linearly with the increase in frequency, as well as this kinetic energy also increases with the increase in frequency. So you can see this graph. So this is intensity is constant, so we get a one saturation current. But here a different frequency, so different stopping potential we get. Now here some definitions you can see. Threshold frequency. Minimum frequency of incident radiation for which photoelectrons are just emitted is called as threshold frequency. This is a very important definition. It is asked in the examination. Threshold wavelength. So wavelength and frequency inversely proportional. So here minimum, it is replaced by maximum. Okay. So frequency replaced by wavelength. So minimum, you can use the maximum. Maximum wavelength of incident radiation for which photoelectric emission are just emitted is called a threshold wavelength. Everything same, instead of minimum, only here maximum. Stopping potential. Stopping potential is what? The magnitude of negative collector potential for which photoelectric current becomes zero is called as stopping potential. So these definitions are already asked in the examination, so you have to remember it. Now let's see the summarization of all the things we learned. Photoelectrons emitted. If frequency of incident radiation greater than threshold frequency. Photoelectrons emitted only when frequency greater than threshold frequency. Now, no photoelectrons emitted if frequency less than threshold frequency. The wavelength corresponding to the threshold frequency is called as threshold wavelength. So that is the as usual. Now here you can see for photoelectric emission, frequency must be greater than threshold and wavelength must be less than threshold wavelength. The rate of photoelectric emission is directly proportional to the intensity. Means photoelectric emission or the photoelectric current directly proportional to the intensity. In another word, you can say. Photoelectrons are emitted with different velocities ranging from 0 to maximum value. Hence, kinetic energy also varies from 0 to maximum value. Maximum kinetic energy emitted of the emitted photoelectron increases linearly with increase in the frequency. Kinetic energy and frequency, they are proportional. And this kinetic energy independent of intensity. It does not depend on the intensity. That also you have to remember. Photoelectric emission is an instantaneous process. So no time lag between this. So it is an instantaneous process. The emission of photoelectrons can just be prevented by applying suitable negative potential to the anode. The magnitude of this potential is called as stopping potential. So we get this relation E into the stopping potential is equal to 1 by 2 mv square. So this is E, charge on electron, V as stopping potential, and this is the kinetic. So remember this relation. Now, failure of wave theory to explain photoelectric effect. Following are the main reason for the failure of wave theory to explain photoelectric effect. According to the wave theory, energy of the radiation depends on its intensity. Greater the amplitude of electric field vector, greater is the energy with its wave. Thus, there should be photoelectric emission. The moment the intensity of the incident radiation exceeds certain threshold value, whatever may be its frequency, but experimentally it is found to be untrue. Experimentally we observe it is untrue. Moreover, energy of the radiation is independent of frequency. Therefore, an increase in frequency of incident radiation should not be affect the velocity or kinetic energy of the emitted photoelectron. However, experimentally it is observed that an increase in frequency of incident radiation increases the kinetic energy of photoelectron. According to the wave theory, the energy of the incident radiation is spread continuously over its wavefront. Therefore, a single electron will intercept only a small part of the energy of the wavefront. Consequently, it will take considerable amount of time to absorb enough energy so as to escape from the metal surface. But experimental results prove that there no time lag between beginning of irradiation and ejection of photoelectron. Now, next article we have to start, and it is Einstein's photoelectric equation. So Einstein explained this photoelectric effect with the equation. And that equation we have to study. So Albert Einstein explained the characteristic of photoelectric effect on the basis of quantum theory, Planck's quantum theory. Now, as per this theory, according to the Einstein, incident radiation contains stream of particles and it is called as photons, or it is also called as quantum. The energy associated with photon is h. The energy of the photon, you remember, h. So where h is the Planck's constant and mu is the frequency. This is frequency that you remember. So when radiation of frequency greater than threshold frequency incident on the metal, there are photon to electron collision. During this collision, electron absorb the energy of the incident photon. And the electron uses this energy in two ways. This is very important. Which energy is E is equal to this h mu. So this energy used by electron in two ways. The first way, you can see here, part of the energy utilized in liberating electron from emitter surface. Means part of the energy used to take electron from the metal surface. So, and some part, remaining part appear as a kinetic energy. So this part means this E is utilized in two ways: to liberate electron from from the emitter surface, and some part is used to give the kinetic energy. So we can write this energy is utilized for two purposes: to give the kinetic energy and to take electron from metal surface. So this equation is what photoelectric equation. The energy of photon is utilized for two purposes: to knock out electron from the metal surface and to give the kinetic energy. To do means for two purposes: to do work to knock out electron from metal surface and to give kinetic energy. And this is the photoelectric equation. The energy required to liberate an electron from atom depends on its position in the atomic shell. Obviously, if electron is situated close to emitting surface, will acquire least energy for liberation. The minimum energy required to liberate electron. So see this, from emitter surface is known as photoelectric work function, or we can represent by phi. So that's why I written here E is equal to kinetic energy plus phi g. So this is the photoelectric equation. So if an electron does not lose any part of its energy to overcome internal collision, it escape the emitting surface with the maximum kinetic energy. For such an electron, the energy of the photon is given by, so you can see this, energy of the photon is equal to, means h mu is equal to kinetic energy plus this work function. Or we can write h mu is equal to kinetic energy, we can write by half mv square, and this is the work function. And this is Einstein's photoelectric equation. Now, Einstein's explanation of photoelectric effect. From Einstein's photoelectric equation, you can see this equation: kinetic energy is equal to, or we can write kinetic energy is equal to h mu minus phi g. So when we are substituting, frequency is equal to threshold frequency, the kinetic energy is coming g, and its work function is coming h mu g. So you can remember this value of the work function to solve the problem. So kinetic energy we can write h mu minus h mu g. So we can write the same equation like this way. So kinetic energy is equal to h mu minus mu g. When radiation of frequency greater than threshold frequency is incident on the metal surface, incident photon impart energy h mu greater than the work function to the electron, causing it to escape from the surface. Thus, photoelectrons are emitted with maximum kinetic energy. If the frequency of radiation greater than the threshold frequency of the material, no photoelectrons are emitted. If photoelectron, so if frequency of incident radiation is less than, so here, less than the threshold frequency, no photoelectrons are emitted. एक minute, here something is missing here. So so this is sentence, huh? No photoelectrons are emitted if frequency less than threshold frequency. That is the sentence. Means here, when frequency less than threshold frequency, we get kinetic energy is equal to h mu minus mu 0. If frequency is less than threshold frequency, we get negative kinetic energy. Negative kinetic energy means no photoelectric emission. As soon as radiation is incident on metal surface, photoelectrons of incident radiation collide with the electron of the emitter. This is similar to the particle-particle collision, in which electron absorb the energy of incident photon and it is ejected instantaneously without any time lag. According to the quantum theory, more intense beam contain greater number of photons incident on unit area per unit time. Therefore, increase in intensity of radiation will increase the number of photon to electron collision. Every photon will knock out an electron, thereby increasing the number of photoelectrons emitted per unit time. Hence, the rate of photoelectric emission directly proportional to the intensity of radiation. Now we learn de Broglie hypothesis. Phenomena of light such as interference, diffraction, polarization can be explained considering wave nature of light. On the other hand, the phenomena such as photoelectric effect, Compton effect can be explained by considering particle nature of light. Thus, light has a dual nature, wave as well as particle nature. Extending this argument, Louis de Broglie in 1924 suggested that matter should also possess dual nature, wave as well as particle. According to de Broglie, all material particles in motion have wave associated with it, called matter wave or de Broglie wave. De Broglie wavelength associated with material particle of mass m, momentum t, moving with velocity v is given by lambda is equal to h by p. You can see this. Or this p we can write mass into velocity. In that formula, h is the Planck's constant that you know. According to the Planck's quantum theory, energy of photon of frequency mu is given by E is equal to h mu, and this mu we can write c by lambda. So we get energy formula by this formula. Using Einstein's mass energy relation, E is equal to mc square, we have this energy E we can write hc by lambda. So we get this formula. So by using that lambda we can write by cancelling the common term, the c and c get cancelled. Lambda we write h by mc, and this mass into velocity is again momentum. So lambda is equal to h by. So here, using analogy of photon as a particle, de Broglie determined the wavelength associated with the material particle having momentum p. Now, de Broglie wavelength of a charged particle. Kinetic energy of charge of mass m moving with velocity v is. Kinetic energy formula, you can see this. By using that, we can write v is equal to under root 2 into kinetic energy by mass. De Broglie wavelength associated with charges. Lambda is equal to h by mv. H by m as it is, and instead of this v, we are written this. Then we are written here under root m upon 2 kinetic energy. Then h, then this m is shifted inside. So we get this h upon 2m into this kinetic energy. Or this kinetic energy also we can write if the electron is accelerated with some potential v, then we can write h upon 2m kinetic energy, we can write E into v. This is also formula. By substituting all the constants also we can write this equation. So if it is an electron, then E into V. If it is another charge, then you can write Q into V for that. So we get this formula for this wavelength of accelerating charge. Now here, if it is an electron, then the value of mass, then value of charge, everything is fixed. H is already constant, except V, everything is fixed. Then by substituting all the values and doing calculation, we get this as a 1.288 divided by root V. So this is in nanometer. So if you want to write this formula in Angstrom, then also you can write lambda is equal to 12.88 divided by root V Angstrom. So after substituting this potential, we get a wavelength in Angstrom. This is in nanometer. So many times questions are asked, so you have to remember this formula for the problem, as well as question may be asked of an expression for wavelength of accelerated charge particle or electron. Then you have to write up this.